prime ij, assuming the original weight is 1, is going to be the probability it's sampled times the weight that it will get, and this is equal to 1. So the expected weight of every edge is 1, and the expected sum of all the weights is going to be exactly the size of the edges. Okay. So now, so this is going to be a generic framework. This is just important sampling if you know this from statistics. So now we need to define how do we choose these probabilities. And we want to do it so we make sure we capture kind of important edges. But the kind of nodes that have lots of really high degree, those are not so important. We might not sample those as with higher probability. Okay, and so we're going to define a quantity called as Dij, which is going to be the minimum of the so Dij is going to be the minimum of the degrees of the two vertices is adjacent to. Okay, so if this is the degree of a vertex, so if I have two vertices I and j, and there's an edge between them, and j has a ton of edges and I only has 3, then the minimum degree of delta of Dij, then Dij is equal to 3, no matter how many edges I have on j. Okay? And then, so I'm going to set Pij equals to the minimum of 1 and t over Dij. Okay, where t again is a parameter, and so where t is going to be equal to okay, so I'm going to set the probability, so it's at most 1, at the minimum 1 here. I don't want to select something with probability greater than 1 because that wouldn't make sense. But otherwise, I have some constant t here. And so this constant t is actually going to be exactly this constant right here. So the number of edges I'm going to have is going to be t, at most t times v log v, or this is t over So this log v and t here is kind of going to be needed to get there's going to be a Chernoff bound like we talked about in the second lecture to get this to work, and I'm not going to go through that, and you're going to need these 1 over epsilon squared samples to make this work. And you need this because you need this to work for all possible cuts. So you need to there's a lot you need to do to cover all your bases, and that's why the size turns out to be so big. So the nice thing about this is that, we're going to see 2 claims here. One is that the expected edges in EV, or this is a lot of e's here, but the expected edges in the new graph here is going to be less than t times the number of vertices. So and that's this t that I chose here as this parameter. And this is true however I set this quantity t here. So, so what's going to happen? So this will be one property. The other property will be that if an edge has less than or equal than t, if a vertice has less than or equal than t edges, then we'll keep all of its edges. Right? So if there's an edge that doesn't have too many degrees, then we don't really need to compress those. We only need to compress the vertices that have tons and tons of edges. Okay, so if the I has degree vi less than or equal to t, then we keep all edges of v. Okay, so this means we've only compressed these really kind of extravagant nodes that kind of have lots of, either lots of links off them, or maybe lots of pages are linking into them, or there's some Twitter account that has lots and lots of followers. These are the ones we're compressing. And for these, we don't really care so much if we're compressing. The other ones, we're keeping all of the edges. So we're not really losing out on most of the kind of the small scale stuff, which really wasn't the problem in the first place. Okay, so you can see why this is true, because if this is t over the minimum of the 2 degrees, so if this was less than t, then t over was greater than 1. So the probability we chose it was the minimum of 1 in this. So we chose it with probability 1, and then you set the weight to 1 over 1, so we didn't even change the weight. Right? So we're keeping everything exact for all the small degree vertices. The only problems are the vertices that are both high degrees, and they each link to a bunch of each other. And this is the part that we're compressing. This is the part that we're sampling. Okay, so now, why is this first property hold? That we know that the size will be most t times this number of vertices. Okay, so this holds because if we can divide the vertices into 2 sets. So we're going to have v small and union v big equals v. And so these small are going to have, all these are going to have degree v less than t, less than t, and these are going to have degree of the greater than t. Okay, so we know that these vertices are not going to get to degree larger than t. And we want to show that these vertices, if we average them over both of these, there's a simple argument that they, okay, yeah, so all the edges, we're going to charge them to the vertex with the smaller degree. Okay, so then we only need to consider the edges here, which are linked to another vertex which has a higher degree than this one. Okay? And so then, if the degree is higher than this, then we keep it. Let's see. Then on those nodes, we should only expect to keep. So then we only consider the edges where the degree is described by the degree of this vertex. So let's say that that in V big we only need to worry about these, and so let's say that the degree here of this V is equal to 100 and T is equal to 10. So then if you look at this, T over Dij is going to be equal to 1/10. Okay, so then I'm sampling each of these vertices, and let's change this to say 200, then I sample with 120. Right, so the expected number of edges for this vertex that I'm going to keep is going to be, each of them is kept with probability 1/10. I multiply this by 200, and I should get back 10, which is equal to T. right? So this is basically the expected number assignment is dij times dij, and this is t, right? So if I only assign an edge to a vertex, if that's the vertex with the smaller degree, then I expect to get at most t edges for each of those vertices. And so then I'm going to get at most t times the total number of vertices. Okay, so if there are a lot of really small degree vertices, then the number I'm going to get is actually going to be much smaller than this. Okay, so this bound is fairly conservative, but it's hard to beat this. There are certain kind of adversarial cases where you actually need to consider this. If there really are a lot of vertices have way too many edges. You know, it'd be interesting to see, and I don't know if this exists, if there's a more tailored analysis based on the distribution of degrees. But okay. And so that's it. Okay, so yeah, so the claim is that if I sample them in this way, I just sample each edge independently, proportional to Pij, which is defined as the minimum of 1 and some value t, where t is set to this, over the degree of the minimum vertex, then I'm going to guarantee with some constant probability this cut property. Okay, where for any cut, I'm going to have a good amount of error. So you kind of need to worry about what you need to worry about is if there are a lot of vertices with slightly more than t edges, then you don't want to kind of miss, and they're all kind of on the periphery of the graph. You don't want to have a cut that just includes all of them. So you kind of need to worry about some special cases, but this should actually work better in practice than what these bounds are getting here. Just deal with some like weird adversarial cases. So this is what I meant by this cut property. But there's actually, if you're thinking graph cuts for kind of, I guess, for spectral clustering, this is kind of what we're after. But we actually have these other sorts of bounds we're doing. We're also trying to do these things where we're using the spectral property to look at the first few eigenvectors to try and kind of do a linear ordering of the edges, or maybe two linear orderings, so then we could kind of draw them in the plane effectively. And there's this other spectral niceness that was going on. And this is not quite capturing that. This is saying something about only the cuts. And there's a more general way of putting this that has a stronger bound. And this was based on, so these stronger bounds are based on the Laplacian of a graph, which, if you remember, there are a couple of ways I had to find the Laplacian. This is a diagonal matrix which just has the degree of the graph on the diagonal, and this is the adjacency matrix. Okay, and this was all that we used for, say, doing PageRank and stuff. But for spectral clustering, we created this Laplacian where we kind of subtracted out the adjacency from the degree matrix. We actually looked at a normalized version of the Laplacian because it has a little bit nicer properties with respect to specific goals within spectral clustering. But there are other people who look at this unnormalized Laplacian, even for clustering and versions of cuts. And so I think some of this can be generalized to other forms of the Laplacian as well, but the most understood results are in terms of this unnormalized Laplacian. Okay, and so then, if you think of this, we also can create the Laplacian for some graph H2, which is a graph H that we approximated. our approximation of G was a graph H, and we can create the Laplacian in the same way here. And it goes through even if you have these weights. Okay, so then, this more general bound kind of wants to say that the Laplacian of G minus Laplacian H, we took the 2 norm, that this is going to be less than epsilon, after we normalize the weights in the same way we did before. So this is, if I match that notation as epsilon, it's the epsilon times the number of edges. And so this is, you probably don't understand what this means. So let me try and write this in a different way, which is basically, so I'll write it this way, and then this statement will be basically equivalent. Okay, so this is kind of a different way of writing this, where x is any vector in R. So it's a vector over the number of vertices you assign some value here. I think it may, oh yeah, because I have both sides, I don't need to do the other. Okay, so these expressions are essentially equivalent. They may be up to a constant, but you can throw into epsilon if you're careful. And so what this is saying is that, so now the thing to realize here is that if x is actually in 0, 1, if this is a 0, 1 vector, then this is equivalent to the cut property. So if it's a 0, 1 vector, this is the cut property. That means that if I laid out all of the vertices in some one-dimensional space, okay, and then I just care about the cut, and these are 0 and these are 1, and so I just said each of these vectors either map to 0 or 1, then this was the cut property that we defined over there. But if I care about essentially where these points are along this line, where this was the first eigenvector of LG, if I care about where they are along the line, then I get this, I need this Laplacian property. Okay? So if I just the cut, then I can do 0, 1, but if I want to kind of understand where they are in the space, I wanted to kind of try and map out this graph to one-dimensional or two-dimensional space by embedding it, then I need to preserve this Laplacian property. And there's a whole industry of analyzing these graphs based on the properties within the Laplacian of them. And I just kind of touched on those when I talked about spectral methods, but there are a variety of other techniques that are built on top of this. So a lot of people really want this Laplacian method instead, this Laplacian guarantee instead, in order to hold it. It really preserves a much richer property. And it's a little kind of hard to understand what's going on here, but think about if you remember from spectral clustering how I did this projection of this graph, I'm really preserving that whole embedding instead of just the property of the cuts. Okay, so this is a goal that people are after often, and that sampling method is not known to actually preserve this. So there's this really cool technique, and I'll just sketch this, and then I'll talk about a completely different way of doing graph sparsification. The way people do this is instead of sampling with respect to the degree, they sample, so that they set Pij proportional to the basically the effective resistance of edge EIJ. Okay, so what you do is you think of this graph as a big circuit, and you think of how much, if each of the edges had a resistor on it, well, if there are multiple edges connecting the same part, then the resistance is diluted a little bit. And so you can define the effective resistance of an edge, and if you sample proportional to that, then you actually gain, you preserve this whole Laplacian property. And so there's this deep connection between the effective resistance and modeling the graph as a circuit and this Laplacian. And this is what you need to understand the embedding and so forth. Now, calculating this effective resistance is pretty hard still. So there's a whole industry of people trying to get something as efficient as that to calculate essentially with respect to the effective resistance. And there are various algorithms. You don't need to do exactly this, but you can kind of approximate this and still get the properties. And there's been a lot of work recently on this. And so, this is not just, people use this not just for graphs, but they use it when they think of these sparse matrices they're trying to simplify. And there's a lot of people who are kind of looking into this line of work. Okay. Okay, so some of this kind of got into the more theoretical realm, but the graphs are complicated, so it's hard to preserve all of the properties of them. And so the best thing people know how to do is this kind of this random sampling approach. If you do something more deterministic, there are often these weird corner cases that are not really covered, and these tend to break things. But if you can find communities or you can do graph compression, then these are effective alternatives. Okay. So if you're dealing with general graphs, then this is basically what is known, but there's a different line of work that deals with spatial rifts. Okay? And so here the game changes a little bit. So now we're going to think of this vertex set as actually being in RD. So it's actually, these are actually points on the plane. And often the distance is defined implicitly, but the edge weight is defined implicitly having to do with this distance and so on. So think of this, now think of this as VR points of interest in the United States. And I want to be able to, so if, what they say is, as the crow flies, a crow can fly from here straight to my house, but I can't drive straight to my house. I have to go on the road, right? So what they do is they try and create a graph that represents as the crow flies, and that's how the road networks in the U.S. work, right? We have these main highways, which are these arteries between cities, and I can't drive straight to my house. I have to go down on one of the main roads before I can get there. Yeah.
So if there is a graph and you are putting it in vertex as points and edges weight as the distance, right? Would it be always possible to switch to something like this? Because a simple graph of 3 vertices may not satisfy the triangle inequality, right? Because the edges weight don't take the guarantee of satisfying the triangle inequality.
Well, okay, so let's see what you're saying here. So I have A,
3 vertices,
and C, and let's say the distance between A, B, and C is the shortest path. So let's say 7, 3, and 2.
Yes.
Okay?
Yes.
So let's say that I want to get from A to C,
Yes.
and I define the distance as the shortest path on the graph. So then the shortest path, actually the distance between A and C is 5, even though there's an edge of weight 7.
Oh, okay.
Right, so this is saying Yeah, I can drive straight to my house, you know, I've got a four-wheel drive, I'm gonna go through a golf course, but it'll actually take me longer than if I drive on the roads.
Yeah. Okay.
So there is a triangle inequality for graph, but you need to reflect the graph edges.
Okay.
Now, if you define these based on the true distance,
You're right.
right, then this distance cannot be longer than the sum of these two, as the crow flies.
Yes.
And then it actually even holds on the globe, right? So let's say, you know, we're doing this for the full US. At that point, the curvature of the globe may actually affect things a little bit. Triangle inequality still holds if you define a graph based on the geodesic distance on the globe.
Right. So you cannot say that the weight of the edges corresponds when you map the graph to the space. Then weight of the edges will correspond to the distance between the points, right? It may be the shortest distance between the points.
Yeah, so I want to, so typically you do map the weight as the true distance.
Okay.
And then you build, but maybe this road doesn't actually exist.
It has to be.
And now I build, the true distance was actually 1,
Okay.
right? And now, but I have to drive on the roads. Right? So the true distance was, or maybe the true distance was 2, but so it took me 2 minutes to get home. If there was a road straight to my driveway, it'd be fantastic, right? But I have to drive the roads, it takes me an extra 3 minutes. Yeah, so this is what we want to do, right? So we're given a set of vertices, they have implicitly defined distances, or sometimes they're actually explicit distances, they aren't all filled in. Maybe there's a large road network planned, and we want to say, well, we're going to get rid of some roads, or we're going to let them kind of get potholes, and no one will drive on them for a while. You know, maybe in some countries that, or if people completely stop paying taxes, right, and the government and everyone was like a nihilist, then and no one maintained the roads anymore, then maybe the citizens would get together and only replace some of the roads and keep those made up instead of, so then you would start with a set of roads and you would choose to maintain a subset of them. Or maybe you'd build new ones, who knows what would happen. It's a crazy thought, huh? Okay. So what we want to do is, so we're going to assume that we're given a graph and the weight of an edge between I and j is going to be the distance between vertex I and vertex j. Okay, and this will be defined implicitly. And so then, and then what we're going to convert it to is a graph into a graph G, which is going to define a distance d of G between I and j, which is going to be kind of the minimum, the length of the minimum path. Okay, and I can define this as minimum of let's say L in the neighborhood set of I, distance from L, vertex L to vertex I, plus the graph distance G from L to J. Right, so I can define this recursively. If I'm at C, I find the minimum distance to my neighbor, which happens to be 2, and then I sum this, it's the minimum of this. So it's this, and that has a graph distance of 3. And eventually, I have the, J is going to be inside my neighbor's set. So if I define the graph distance like this, it works as, it satisfies the triangle inequality. It's going to be a metric unless there's an edge of weight 0. And assuming that each edge you can walk either direction.
Can you always plot this in 2 dimensions?
Well, not necessarily. So if the vertices start in higher dimensions, then you may not be able to. So actually this is, I mentioned briefly in the, I think like the PCA lecture or the SVD lecture, there's a problem called multidimensional scaling, MDS, and that's where you're given a set of distances between vertices, any distance matrix, and your goal is to kind of embed it in 2D, preserving the distances as good as possible. And basically what you want to do is convert this into essentially some similarity matrix instead of the distance matrix, and then do PCA on that, and use the top two principal components, top two singular vectors, and that'll embed it as good as possible under some measurement. And that's basically the kind of classic MDS thing. But there are other techniques for that. So not always. But if your vertices start out in R2, then you always can. Except that your edge is just going to be a subset of the edges. Right? So if they start out in R2, you draw them exactly where they are. So there's different problem scenarios. Sometimes you're just given the distances, sometimes you're given the distances some way implicitly. Okay, so now the goal is to construct, so assume that this graph is actually the complete graph as the input. And then the goal is to get a graph H such that okay, so I want the ratio of these edges. So if H is a subset of G, it's fewer edges, then the distance will only be longer. So we start, and G is the initial graph. Either it's given explicitly, or it's given as a implicit input of all just the points. And then H is going to be one with a smaller number of edges. And so its distance is only going to be larger. But we don't want it to be too large. We want it to be, it's 1 plus t factor. So if t is 1, then it's going to be no more than twice as long to get there. So if I drove twice as fast as the crow home, then I would always get home at least as fast as the crow. So and so then if this is true, then H is called a t spanner of G. So that's just the technical term for this, the t-span. And so people not only want a small number of edges here, but they also want kind of the total length of the graph to be small. So you don't want to have, say, like 7 different roads from here to Vegas. Maybe it's one long road, it's one edge. But I don't want 7 different ways. I only need 1 road going to Vegas. Or maybe there's another road. I don't know. I assume there's only one road going straight to Vegas. Are there any back roads? Okay, in case I'm ever on the run from the cops or something. Okay, let's pretend I didn't say that. You gonna edit that out, Lisa? No. Okay, so we don't want the total length to be too big, and we also don't want too many edges coming from any one node. The reason for this is often when you're doing certain algorithms, they often depend on the degree of the node, or you don't want one intersection getting too much traffic. Right? This algorithm, the sampling algorithm, it depended on the degree. If all the degrees were bounded about equally, then it would actually work much better than it actually does. So you want to keep the degree of these small as well. Okay, so 5 minutes left, so let me quickly give you an overview of kind of the 3 ways of building these t-spans. The first way is greedy. So what I'm going to do in the greedy way is I'm going to look at all of the potential edges of my graph. So all of these pairs, and I'm going to sort them from smallest to largest. And then I'm going to look at the shortest path on the graph in between these two vertices if it's already connected. If it's not connected, I add the edge. If not, I look at the shortest path on the graph. If the shortest path between some I and j satisfies this equality, then I don't need to add the edge. And in fact, at that point, so I forget, I don't have it in my notes. I think you can actually stop as soon as you have one thing that doesn't violate it, but that may not be true. But you just keep adding these edges from smallest to largest, and this will actually work very well. So just add them in a greedy way. The problem is it's very slow. I have to actually consider all of these edges, or I have to sort them by distance. And you can probably actually, you mainly just need to sort the close ones, but this will actually give some pretty good results. But people don't want to do it because it's a little too slow. The second way, it also doesn't have like the property where you could have one vertex that has a really high degree. So it's not going to guarantee anything about that. The second way is based on the cone property, and that's the idea that you have these vertices. Okay, so if I'm looking at this vertex here, I probably don't need an edge here. I can go through one of these other vertices. And I don't need an edge here. I can go through this vertex. So what I do is I divide up, and this works really well in 2D. I divide up the space around each vertex into 6 cones of 60 degrees each, or you could do 7 or 8 cones. There's kind of some work on how many cones do you need. In some cases, I think you can get down to 4, but 6 has some other nice properties. And then you take the closest point. You draw like an arc, and I take the closest point and I link to this. So I add in, let me draw this in a different color. So I add in this edge here to the closest point. So the more cones you draw, the better the value t is here. And if you don't make enough cones, it may not be connected. So you think you need at least 3 or 4. There's some open conjectures on this. But if you do 6 cones, it works pretty well. You just do the closest one. Now, if I want to get to this